Smith from the University of Washington, who's going to speak about a classification of three Calabi-Yau algebras.
Well, first of all, many thanks to the organisers for inviting me. I'm learning a lot at this conference and really enjoying it, so thanks. And thanks especially for asking me to speak on my birthday and arranging the dinner on my birthday too. It's all very nice. I feel special. Thank you. Okay. How does this work?
Pushing the wrong button.
What's that? Or do I have to turn this? No, is it on?
This all has to be on.
It is on.
It is on.
Holding it the wrong way. That way.
Yes,
Yeah.
here.
Oh, thanks.
That's forward and that's back.
Thanks. Yeah. Okay, this is a report on joint work with Izuru Mori. We address the following problem. It can be stated several ways, but since we've had some quivers appear in the last yesterday, I thought I'd state it this way. Let's take a very simple quiver, one vertex, three arrows. Associated to it is its path algebra, and the question is when to find those homogeneous degree 3 superpotentials, that's elements of degree 3 in the path algebra. Whoops. Oh, I've got it. Yeah, elements of degree 3 in the path algebra, such that this algebra here, oh, that should be a round parenthesis, is 3 Calabi-Yau. I'm going to restate the problem.
Can I ask a couple of questions?
Yeah.
First is, why do you call it superpotential?
The physicists use the word superpotential, so I'm following their convention
Does
there.
that come from matrix models? Or?
No idea.
No, that's a difference.
No idea. I'm going to restate the problem in a more down-to-earth way.
Is it super in some sense of graded? Is
No,
that too graded?
no. Just ignore that formulation of the problem.
So
Okay, let's get
well,
just pure mathematics.
The other question was, I may have missed it because there's been a lot of talks that I've unfortunately missed. Why Calabi-Yau? What's the connection with
I'm going to define Calabi-Yau, and I'll say a few words about that.
connection with Calabi-Yau manifold?
Very closely related. Yes. Okay, so the algebraic formulation of the problem I want to talk about is this. We start with a field K. Just think of the complex numbers. And a graded algebra over that field. That means there's a vector space decomposition. And these whoops, wrong button. And these components, called the homogeneous components, satisfy this. Elements of degree I times elements of degree j have degree I plus j. The opposite algebra, just change the multiplication, and we can define, as Karen did yesterday, what's called the enveloping algebra, tensor of a product of these two things. And A can be viewed as a left module over this in this way. And that's just another way of saying, think about A as a bimodule. So, yeah, an element in the enveloping algebra times C is given by this formula here. So that's viewing A as a bimodule. If you've got an automorphism of A, and I'm only interested in automorphisms that respect the grading, preserved degree, nu, then we can form another left module of the enveloping algebra where we twist the multiplication on one side by this. So same formula, but just twist by nu here. And we say that A is twisted Calabi-Yau of dimension D if it has a finite length projective resolution as a module over AE, i.e. a bimodule resolution by finitely generated projectives, such that there is an isomorphism of bimodules, or equally well, we're viewing A as a left AE module, so this inherits a structure of a right AE module. If this right AE module is isomorphic to this thing here, and I suppose I've got my left and rights mixed up, but anyway, okay. It's isomorphic to A as a bimodule, except twist on one side. This X group should vanish in all degrees except degree D. And in that case we say that A is twisted Calabi-Yau of dimension D. And the L here is just that we're working in the category of graded modules, and the L just shifts the grading, and you can ignore it. But just to be precise, put it in. And we say it's Calabi-Yau rather than twisted Calabi-Yau if this nu here is just the identity on A. So Calabi-Yau is the condition that this thing here vanish everywhere except in 1 degree D, top degree, and there as a bimodule it's isomorphic to A. We then say A is D Calabi-Yau. The polynomial ring in D variables is D Calabi-Yau and is essentially the only commutative Calabi-Yau algebra. So Calabi-Yau algebras are non-commutative things for me. A nu or nu inverse in Karen's talk is called the Nakayama automorphism, and that problem I formulated at the beginning can be restated as follows. Let's take the free algebra on 3 variables, x, y, and z, the free algebra, and take 3 linearly independent elements of degree 2 in the free algebra and quotient by the ideal they generate. And the question is, classify these algebras that are 3 Calabi-Yau. So for example, the polynomial ring in 3 variables x, y, and z, you'd mod out the commutators xy minus yx, yz minus zy, etc. And that's 3 Calabi-Yau. And to be precise, I need, in what I'm talking about, the field to be algebraically closed and have to exclude characteristics 2 and 3. Okay, and so the first theorem I want to state is that these 3 Calabi-Yau algebras up to isomorphism have quite a nice presentation. If A is 3 Calabi-Yau, there's some degree 3 polynomial f and some scalar lambda, which I allow to be infinity, such that the relations are given by these rather simple forms here. Now, I'll say exactly what this fz hat is. Fz means the partial derivative of f with respect to z. That would then be a degree 2 element in the polynomial ring, homogeneous of degree 2, and the hat is a symmetrization of that. You see, we're working in the free algebra. We're imposing this relation in the free algebra, so we just have to symmetrize. So if, for example, fz was yz, then this hat of yz would be yz plus zy. Well, a half that, really, but there we are. So the other thing I want to point out about these is that at lambda equals 0, you just get the polynomial ring. And that is the key to the fact that this algebra here, when lambda is not infinity, is a deformation quantization of the polynomial ring with respect to a suitable Poisson bracket that I'll make explicit on the next page. So most of these things are deformation quantizations of the polynomial ring. That's a surprisingly nice answer. And the converse is more or less true. If we take such an f, take a degree 3 polynomial f, and form this algebra here, then this is Calabi-Yau almost always, except for 2 lambdas. That's when lambda's in K, and there's a slightly more complicated formulation when it's Calabi-Yau when lambda is infinity. So lambda infinity just means the relations are f hat, fz hat is 0, fx hat is 0, etc. Okay, so yeah, this thing is the symmetrization. I've told you what that is. The fact that this is a deformation quantization of the polynomial ring is due to Donin and Mikhail Lamanov, who studied these algebras 20 years ago or so. And it's a little tricky to prove it is a deformation quantization. And the Poisson bracket, with respect to which it is a deformation quantization, is given by this simple formula here. For example, the Poisson bracket of x and y is just the partial of f with respect to z. Now, there are deformation quantizations due to Kontsevich, very complicated ones, and these things I should point out are not, in general, Kontsevich's canonical deformation quantizations. Occasionally they are, but in general they're not.
But you have subscript f? What do you mean by?
Oh, I just, the subscript f on the Poisson bracket is just to say that this Poisson bracket is that coming from f by these formulas. Yeah, I don't need it for this talk, that subscript. Okay, now this theorem on the previous screen doesn't really answer the first problem that I stated, which was to classify those superpotentials that give you a Calabi-Yau algebra. And I'm going to come to that problem in a few slides from now, but I just want to say that in advance that the conditions on W, the superpotential that ensure the algebra is 3 Calabi-Yau, are geometric conditions, and this theorem here gives a hint of that. So we've got this f which determined these algebras A, F, lambda, and we can think of f because it's homogeneous of degree 3 as giving us a form of degree 3 on the projective plane, and we can, I'll write E for its 0 locus. So in the case where that E is smooth, and hence an elliptic curve, this AF lambda is Calabi-Yau for all lambdas. And there are a couple of values where it's not Calabi-Yau, in the cases where that 0 locus is a triangle, or a conic with a transverse line, or a nodal cubic. And then when we come to more degenerate E's, like a triple line or a double line and a line, 3 lines through a point, conic and tangent line, or cuspidal cubic, then this AF lambda is always Calabi-Yau, as in the smooth case here. And this dichotomy, or as we'll see later, we should view this as a trichotomy, 1, 2, and 3, is a trichotomy that's very familiar within algebraic geometry. E is a stable curve, that's this case 1, semi-stable but not stable, neither stable nor semi-stable. So anyway, the way it breaks down is quite familiar. Okay, so I want to go back to that first problem, for which superpotentials, i.e. degree 3 homogeneous things here, is what I'll call the Jacobian algebra, and I'll define in a moment, 3 Calabi-Yau. And in the physicsy literature, Jacobian algebra is usually superpotential algebra. Just so we've got a translation there. Now, starting point now is a theorem of Bocklandt. I'll state a very special case of it, which says that if an algebra like this is 3 Calabi-Yau, then it is in fact a Jacobian algebra, a superpotential algebra, and I'll explain what that is in a moment. So the problem really is to classify those degree 3 W's such that this J of W, which I'm going to define as 3 Calabi-Yau. And this problem here, i.e. when is this 3 Calabi-Yau, is a baby case of a much bigger problem. And to tell you what that bigger problem is, I need to give you the general version of Bocklandt's theorem. His theorem is this. Let's suppose this graded algebra is just a product of copies of degree k, a product of copies of k in degree 0, and it's generated as an algebra by its degree 0 and degree 1 part. Well, if such an algebra is 3 Calabi-Yau, then there is a quiver, directed graph, finite, as in Ueyama's talk, such that this algebra A is isomorphic to a quotient of the path algebra by the ideal generated by what are called the cyclic partial derivatives of W, and I'll define those in a moment. And so in light of Bocklandt's theorem, the following problem is very natural. Classify those Q's and those homogeneous W's in the path algebra, such that this Jacobian algebra is 3 Calabi-Yau. And there are many, many examples of this in the literature, pioneered by the physicists, but very little is known about any kind of classification. So for that reason, it is sensible to look at this baby case that I'm going to talk about and just settle the question there. Okay. Okay, so I'm going to think about a situation where I have the free algebra on 3 letters x, y, and z, and an element w that, first of all, is just a word in x, y, and z. By that I mean it might be something like z squared xy, z x. Anyway, the cyclic partial derivative of this w with respect to x is defined by this formula here. Now, let's just think about what our calculus students do when they want to differentiate a polynomial. They just see n and replace it by n minus 1 and bring the n down. In effect, they're deleting an x. And then they've got, right? And so what would happen, what would we get if we applied this formula to x to the n as an element in the free algebra? Well, we sum over all factorizations of x to the n, and there are going to be n of those factorizations, and we move the last part of the word to the front after deleting the x. So when we take one of those n factorizations, we just delete an x, and we get x to the n minus 1. There are n factorizations because there are n x's in this word, so we'd get n x to the n minus 1. Lo and behold, the usual derivative. But anyway, we're doing this in the free algebra, or more generally in a path algebra, where instead of just x, y, and z, we have things for one for each arrow. And we extend this thing linearly. We call that the cyclic partial derivative. Of course, there are partials with respect to y and z. And then the Jacobian algebra is defined in this way here. We just take free algebra and mod out by the ideal generated by the cyclic partials. And the ideal depends only on w, not on the choice of basis for the degree 1 part of the free algebra. Okay. Now, to answer the question, when is it 3 Calabi-Yau, I need to introduce some things. C and S are maps here, and I use the letter C because it's sort of a cyclic average. If I take elements of degree 1, P, Q, and R, then C of their product, P, Q, R, is this, the average of what you get when you cycle around the P, Q, and R. And S is sort of the symmetric average. We take all of these ways of permuting the letters. We take 1/6 of that. Now, the important thing for this classification are not C and S on their own, but rather their difference. And it turns out that if W is any word, any element in degree 3 of the free algebra, then C of W minus S of W is a multiple of this, C of XYZ minus S of XYZ. And that multiple I'm going to call lambda of W. Okay. The other ingredient I need, apart from lambda, is, of course, the free algebra maps onto the polynomial ring, and that W will give us an element in the degree 3 component of the polynomial ring. I'll call it W bar. I'm going to define E to be the zero locus of W bar, and I always mean the scheme. So most of the time, that scheme will be a cubic divisor in P2. Of course, occasionally it will be P2 itself. That's one geometric ingredient. The other geometric ingredient, also usually a cubic curve in P2, I take the vanishing locus not of W bar, but this rather complicated expression here. The Hessian, the determinant of the 3 by 3 matrix of second order partial derivatives, and I add 12 times the square of the scalar, lambda here times W bar. This expression here is a cubic polynomial again. and I take its vanishing locus and I call that E prime. And although the Hessian will change as I change the basis x, y, and z, the zero locus of this thing, and lambda will change too as I change my choice of x, y, and z. The zero locus of this is independent of the choice of basis. So in general, we have these two cubic divisors in P2 associated to W. Oh, okay. My slide. I've got to turn it on. Now, I made this because I thought perhaps when I took this thing here, it might be too small. But that's smaller. Okay. So look at this one instead of that one. Anyway, here's a table which sets out exactly what happens. Now, the zero locus of this W bar could be P2, a triple line into line, 3 lines through a common point, conic with tangent, cusp. Now, if this thing C of W is equal to S of W, then the J of W is never Calabi-Yau. However, if C of W is not equal to S of W, it's always Calabi-Yau. For these curves, these cubic divisors here, C of W equal to S, it's always Calabi-Yau. And when the condition is not satisfied, whether it's Calabi-Yau or not depends on what E prime looks like in these two cases. And in this case, where the zero locus of W bar is a triangle, it's Calabi-Yau if and only if the Hessian is related to the original W bar by this formula here, a rather startling formula. I don't know why it appears, really, no deep idea why. And of course, the generic case would be when the zero locus of W bar is smooth, i.e. an elliptic curve. And again, we have this dichotomy between this and this. And surprisingly here, it's always Calabi-Yau, except when the J invariant of the elliptic curve is 0. So Calabi-Yau. And when we have this, the generic case, it's always Calabi-Yau. So that's the way it sort of depends on some geometric things. So I think that if one is trying to tackle that big problem for which Q's and which W's in the path algebra, this J of W is Calabi-Yau, through Calabi-Yau, it's a very difficult problem because you're going to have to deal perhaps with some replacement for these geometric conditions.
So which of these cases is the most common in
the elliptic curve case, and this is the generic case here. Elliptic curve, generic cubic curve is elliptic, so always Calabi-Yau. So
in the physics literature, this is mostly the most common then?
That's right, that's right. And Raf pointed out in his paper that that the J of W Calabi-Yau is the generic event that occurs. Okay. Some other things. So we had the J, and we had these AF lambdas, and how are they related to each other? Well, this AF infinity thing is J of F hat, the Jacobian algebra of this. In this column here, the algebras that are the Calabi-Yau algebras appearing in that column are these guys from the earlier thing, and these always turn out to be Clifford algebras. It's nice. Clifford algebras over a polynomial ring in 3 variables. Clifford algebra of rank 8, what it's worth. In this column here, the Jacobian algebras are these deformation quantizations here. And I should also point out that when this Jacobian algebra is 3 Calabi-Yau, its homogeneous components have the same dimension as the polynomial ring in n variables. So these J of W's are sort of non-commutative analogues of the polynomial ring in 3 variables in many strong senses. Okay, I don't know, let's run through this really quickly. If J of W is 3 Calabi-Yau, it's also what is called Artin-Shelter regular. I don't want to get into the definition of that, except to say that the key part of the definition here is a homological condition that's very much like the Calabi-Yau definition in terms of the vanishing and non-vanishing of those X groups. These things are Noetherian. They have no zero divisors. And when this is not Calabi-Yau, it must in fact be isomorphic to one of 9 particular algebras, right? One of 9 particular algebras. And let me point out just this case here, draw your attention to this case. If that vanishing locus of W bar is an elliptic curve with J invariant 0, you can choose the basis such that that curve is the 0 locus of this polynomial, x cubed plus y cubed plus z cubed. So W bar, or W rather, could be taken to be this. This is W bar, but you could equally well take W to be this, now thought of as an element in the free algebra. And when you take the cyclic partial derivatives of this, you'll get 3x squared, 3y squared, and 3z squared. We're not in characteristic 3, so in effect, it's the free algebra modulo these 3 relations here. When the 0 locus is an elliptic curve, the generic case, these Jacobian algebras, the Calabi-Yau algebras, what are called Slianon algebras, 3-dimensional Slianon algebras, and in Vaughan's talk he mentioned Slianon as coming from the school of Fadeev in Leningrad, and Slianon at that time studied some algebras which are now called 4-dimensional Slianon algebras. These are the 3-dimensional ones which can be defined in a very similar way. Okay, let's ignore that. I'm going to skip that because I'm a bit concerned about time. Okay, and I should, okay, yes, I just want to mention that if instead of taking that quiver with 3 arrows in one vertex, one took 2 arrows in one vertex, and now formulated a similar problem, when is that, oh, I shouldn't have a 4 there. Okay, in this case, one should look at quartic, degree 4 superpotentials, and ask the question, when is this free algebra quotiented by those 2 cyclic partial derivatives, so 2 cubic relations, when is that Calabi-Yau? And there's a very similar outcome to the classification by Mori and Ueyama. You get, again, deformation quantizations of the polynomial ring in 3 variables, but one should now give this a grading in which z has degree 2, and now there will be a degree 4. Oh, I missed out a z here. A degree 4 polynomial, such that the deformation quantization for a Poisson bracket given by this formula here. And the E and E prime, the curves that govern whether or not it's Calabi-Yau, are now curves on, instead of P2, on this surface, P1 cross P1. And again, these are the analogs of the cubic curves in P2. And, you know, German mathematicians classified all these curves and so on way back in the 1800s. So all very classical stuff. Okay, right, first up. I now want to talk about the Calabi-Yau algebra that has nothing to do with the problem I've already formulated and discussed. I want to discuss one very special Calabi-Yau algebra, 3 Calabi-Yau algebra, and I want to explain how it's related to G2 holonomy. Okay, so let's start with the question of why care about 3 Calabi-Yau algebras. Calabi-Yau algebras can be used to construct what are called Calabi-Yau categories. These are triangulated categories with a certain very well-behaved additional structure, which Ueyama touched on in his talk yesterday. These triangulated categories have a very distinguished autoequivalence called the Serre functor, which is related to Serre duality. And the Serre functor, the Serre functor, when that Serre functor is just a translation, you know, you've got this part of the structure of a triangulated category is you have this shift or translation. If that Serre functor is just some power of the shift, then you call this a Calabi-Yau category. I can now answer your question, Vaughan. If you've got a compact 3 Calabi-Yau manifold, then it is a projective algebraic variety, a smooth projective algebraic variety of dimension 3. You can look at the category of coherent sheaves on that variety, pass from that category of coherent sheaves to its derived category, that is a triangulated category. And the fact that that variety is a Calabi-Yau manifold says that the Subfactor will be just the shift by degree 3. Yeah. So Calabi-Yau manifolds are algebraic varieties where the triangulated category of derived, has this very nice property that the Subfactor is a shift. And these Calabi-Yau algebras generally give rise to categories with that property.
So the Calabi-Yau manifolds give commutative Calabi-Yau algebras, is it?
No.
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 No such luck.
No such luck. Yeah, no such luck. Okay. Anyway, Calabi-Yau categories are often used by mathematical physicists as a setting in which to talk about D-branes. Okay, so I now want to get to this G2 holonomy. Now in string theory, space-time is the base for space itself, which is either a 10-dimensional manifold or an 11-dimensional manifold. Now, when it's 10-dimensional, some string theory considerations say that the fibers have to be compact Calabi-Yau manifolds of dimension 3, of course. When it's 11-dimensional, those fibers have to be compact 7 manifolds. So these are real differentiable manifolds. These are complex manifolds. And they're 7 manifolds with this additional structure, very special structure, what's called G2 holonomy. Now, I don't know any differential geometry. I can spell the words, but that's about it. So I won't say much about that. Now, some years ago, I encountered a 3 Calabi-Yau algebra, which is generated by 7 elements. So we take the free algebra over the reals, I'll come back to why the reals are important here, on 7 variables, modulo 7 relations. These 7 relations. Now, of course, these should make no sense at all. But I'll make sense of these soon. But anyway, at present, let's just observe that because these relations are sums of linear combinations of commutators, when we mod these out, then this thing here will be the enveloping algebra of some Lie algebra. Take the free Lie algebra on x1 through x7, and then impose those additional relations, you'll get a Lie algebra, and it'll be an infinite dimensional graded Lie algebra, and this thing modulo those relations. So the Calabi-Yau algebra I want to talk about is the enveloping algebra of some infinite dimensional Lie algebra. And it turns out that this 3 Calabi-Yau algebra, its automorphism group, contains a copy of the exceptional Lie group G2. This will be here the compact simple Lie group type G2. Okay, up. Yeah. So this diagram here is a way in which you can organize this data and remember it. One of my colleagues, who's a differential geometer, said to me that in the theory of G2 manifolds, there's a very special 3 form that appears. And there are a lot of indices in the expression for this 3 form, and who can remember, there are signs, +1, -1. He says, how can you ever remember these? Well, you could remember these if you know about the Fano plane, the projective plane over the field of 2 elements. And you can label the points. There are 7 points in this Fano plane, and there are some lines, and this configuration one sees often, and one can use this as a mnemonic device for remembering those relations a couple of screens ago, or remembering what this distinguished 3 form is that turns up in G2 holonomic. But anyway, we'll just skip that.
Where is 7?
What?
And boom.
7 points in the Fano plane, P2.
7's in the middle. It's in the middle.
It's in the center.
Oh, yeah. 7 is the middle point. Yeah, 7 is here. Yeah. I just, my tech skills were at their limit. Okay, right. So let's go back to this algebra. So by Bocklandt's theorem, that will be the Jacobian algebra, superpotential algebra, for some superpotential. And I'm just saying, I guess, V here is the linear span of the x's, and it'll be a degree 3 homogeneous element in this free algebra, hence in the 3rd tensor power of that. Now, let's come down to here, where we take this element of degree 3 in the free algebra, linear combination of these pure tensors with coefficients epsilon I, j, k, and it's these things that are difficult to remember. These things are 1 when the indices are these, and you've got then some S3 behavior, which will tell you, if you remember these ones, what the other ones are. But anyway, it's kind of hard to remember these 7 distinguished triples. Anyway. Now, I came across this algebra because almost 10 years ago, I was giving a talk in Santa Barbara, and there was a physics PhD student, Richard Eager, who was attending my talk, and afterwards he came up to me. My talk was about Calabi-Yau algebras and Kurzula, I can't remember, Kurzula algebras or something. And he said that he knew this paper in the Journal of High Energy Physics, in which a certain superpotential appears, this one. My talk wasn't anything to do with this at all. And he asked me, is this Jacobian algebra associated, well, he said, superpotential algebra associated to this superpotential Kurzul? I said, well, why would you think it's Kurzul? And he gave me an answer which didn't help me. He said it's because the Bose fermion corresponds. So I set out to just try and figure out if this algebra was Kurzul. And it turns out it is. And that's a good thing. Anyway, many thanks to Richard Eager. Okay, I want to give a definition now of this algebra, which I said, so I wrote down those relations, kind of meaningless as most relations are. I want to give a description of this algebra in terms of the octonions. I said this algebra is very special, and it's very special for the reason that the octonions are very special. The division algebras over the reals, the complexes, the quaternions, and then, if you throw away associativity, the octonions. And whoever thinks about the octonions? I've never thought about them. And there's a beautiful article by John Byers that appeared in the Bulletin 10 years, maybe more ago, about the octonions. He referred to them as they're like that crazy old uncle who lives upstairs in the attic. We all know he's there, but we don't talk about him too much. Okay, so the octonions, that's an 8-dimensional real vector space with a multiplication such that every non-zero element has an inverse, but it's not an associative algebra. Just over 100 years ago, Élie Cartan proved that the automorphism group of the octonions is this exceptional Lie group of type G2. Now, one has a notion of imaginary octonions, purely imaginary, just as purely imaginary quaternions, purely imaginary complex numbers. It's a 7-dimensional vector space here, and because it's acting as algebra automorphisms, the G2 action on the octonions sends the imaginary octonions to the imaginary octonions. So G2 can be realized as a subgroup of GL7R, just this 7-dimensional vector space. Now, let's have a look at this diagram. We have the multiplication on the octonions. We have the projection to the imaginary part. Inside the tensor product of the octonions themselves, we have the tensor product of the imaginary octonions with themselves. Let's compose these three arrows, and let's call that linear map mu. Now I want to look at the dual of this. Take the dual vector space. So mu star is the dual, it goes back this way. Now, I can, on this 7-dimensional vector space, I can take the tensor algebra on that, the tensor algebra on this. So this is the free algebra on 7 variables. And the degree 2 part of this tensor algebra is this tensor product here. And I can now look at the image of this, a 7-dimensional subspace of this, and quotient out the two-sided ideal generated by the image of this map here. Now it turns out that this algebra here is the algebra A that I wrote down a few screens ago. So it has a very nice formulation in terms of the octonions. Now because G2 is acting on the imaginary octonians, all this construction is equivariant, we get an action of G2 as the automorphisms of this quotient here. And in fact, we could formulate a description of this algebra where we don't mention the octonions at all. We just talk about G2. G2 has a 7-dimensional irreducible representation, V. Inside the second tensor power, V is a subrepresentation which is isomorphic to V, a unique subrepresentation. And so if we take inside V tensor 2, this unique 7-dimensional subrepresentation here, and quotient out the ideal generated by that, we get A. So I don't need to talk about the octonions, but the reason to talk about the octonions is to explain why this algebra is so special. It's special because the octonions are special. Okay, now these epsilon ijk's that I used in the definition of the superpotential that gave rise to this algebra A, these could be thought of in some sense as structure constants for the multiplication on the imaginary octonions. Okay, so here's our list of division algebras over the reals. Now I'm going to, this construction that I gave of J of W on the previous screen here in terms of starting from this diagram, well, we could write down a similar diagram where we have, say, the quaternions here, right? We have the purely imaginary quaternions, we could do the same construction here and get out some algebra associated to the quaternions. What is that algebra? Well, if we do that for the quaternions, we get the polynomial ring in 3 variables over the real numbers. Another 3 Calabi-Yau algebra. So this guy's 3 Calabi-Yau, this guy's 3 Calabi-Yau. And you know, once you get into it, you might as well do it for the complex numbers. This recipe on the previous screen will produce the polynomial ring in 1 variable. Now, I mentioned this thing is Koszul. A Koszul algebra has a Koszul dual, as Alistair talked about yesterday. And what are the Koszul duals of these things? Well, I've written them down here. The first 3 are exterior algebras on 0 variables, 1 variable, 3 variables, and then this Koszul dual here is a graded algebra in degrees 0, 1, 2, and 3, and we have 7-dimensional things here, and we could write down the multiplication for this algebra in terms of quaternions, octonions. Okay. Some other properties of this algebra. It's not a Noetherian algebra. It's very big. It's got sort of exponential growth. But once you get away from Noetherian rings, there is another finiteness condition that is often useful to impose, and that is the notion of a coherent ring. And it turns out that this J of W is coherent. I don't want to go into the definition of coherent, but the point is this, that if an algebra is not Noetherian, the category of finitely generated modules is no longer an abelian category. You don't have kernels. However, if you've got a coherent algebra, there is a replacement for the category of finitely generated modules that is abelian. So it's good to have an algebra that is coherent. Now, a rather surprising fact about this Calabi-Yau algebra is that it's related to an algebra that Kohn and Dubois-Violette studied a long time ago in the 90s, which they called the quadratic self-duality algebra. And I think it turned up in some work of theirs to do with what they called a Yang-Mills algebra. Now, let me just say that this surjective math here, the geometry associated to G2 manifolds is extraordinarily rich, and in part it's because the structure of the octonions themselves are extraordinarily rich. And if you read the very beautiful book by, I always forget, Harvey and Lawson, I forget what it's called, you will learn a lot about the octonions. I was very surprised that the differential geometers seem to know more about the octonions than most algebraists. But inside the octonions are many copies of the quaternions. And if you take a three-dimensional subspace of the octonions that is the purely imaginary part of some copy of the quaternions inside the octonions, and you quotient the ideal generated by that imaginary part of that quaternions, you get this quadratic self-duality algebra. I don't know if there's any significance to that. Since people have been talking about pre-projective algebras, there are some pre-projective algebras related to this J of W. If I take a subalgebra generated by 6 of those 7 xi's, that is the pre-projective algebra for this quiver here. Similarly, if I mod out one of these variables, the ideal generated by one of these xi's, that too is isomorphic to the pre-projective algebra on this quiver. I don't know if there's any significance to that, but anyway, I thought I'd mention it. Okay, time to get to G2 manifolds, and I hope no one asks me any questions about G2 manifolds. Please. Okay, so G2 holonomy. Now, in G2 holonomy, which is something to do with 7 manifolds, so the tangent space will be, at each point will be R7, of course, isomorphic to R7 because it's 7 manifold. There's a in wedge 3 of R7, or wedge 3 of the tangent bundle, I should really be saying, there is, or cotangent bundle, there is a very distinguished 3 form that is defined in terms of these tensors that I almost defined on the other page. From a more geometric point of view, or more algebraic point of view, GL7, of course, acts on wedge 3 of R7, and there's a unique dense orbit. And it's the orbit of this guy, and the stabilizer of this guy, under the action of GL7, is G2, sitting inside GL7. Now, I'm going to rush through this. We have a notion of a G2 structure on the manifold, and that involves some principal bundle that is, whose structure group is G2. Now, this G2 structure gives rise to a 3 form on the manifold and a metric G in such a way, I should have said cotangent space, in such a way that there's an isomorphism of that cotangent space with R7 with the property that the phi, this 3 form, identifies with this phi 0, and the metric G identifies with the sort of canonical metric on R7. Okay, right, so this data is called a G2 structure, and the theorem is that if you've got a torsion-free G2 structure, let's forget torsion-free on a compact 7 manifold, then the holonomy group is exactly G2. And this is a condition that appeared a few screens ago when I talked about 11-dimensional space fibered over Minkowski space, with the fibers being these G2 manifolds, 7-dimensional manifolds. Anyway, so we have this, if you look, so you can, a good place to read about G2 manifolds is in Joyce's, Dominic Joyce's talk at the International Congress in 2002. And Joyce was the first person to construct manifolds, compact manifolds with G2 holonomy. Robert Bryant had constructed non-compact manifolds, and this was a big deal. First Bryant's result was a big deal, and then Dominic Joyce's examples were also a very big deal. And if you look now at examples of compact manifolds with G2 holonomy, you'll see some very interesting ways in which they're constructed some of which are related to 3 Calabi-Yau manifolds. Now, this algebra sort of brings together, because the algebra is 3 Calabi-Yau and because of the superpotential that defines it, that these tensor, these structure constants, these epsilon ijk's, are the same for the 3 form up here and for the, this sort of brings together both the G2 holonomy world and the 3 Calabi-Yau world in one single algebraic object. And I find that quite interesting myself. Well, that's a good place to end. So thanks for listening.
Any questions?
So I just had a comment about, I was very intrigued by these superpotentials, and I was surprised that the answer to my question was completely no. I mean, you could use these superpotentials as potentials in matrix models, and it might be interesting to look at that because in the matrix models, all these cyclic derivatives are very important for
Well, I'd love to talk about that with you. Yeah, I knew nothing about that. That sounds very interesting.
Just a comment about your construction from the Ontitonians. The tensor square of that 7-dimensional representation of G2 actually has 4, it's multiplicity free, it has 4 representations in it. So in principle, you could construct algebras for any one of the 4.
Yes, you could. Yes, I had not thought about that. Yeah, just take the ideal generated by that irreducible
Correct.
thing. Yeah, that sounds interesting.
Some of them are undoubtedly known. I mean, the trivial representation is one of them. It's self-dual, so that's not so interesting, but
Yeah,
the others are. I mean, the adjoint representation, for example, is
It
in
would be
there.
interesting.
4-dimensional.
Yeah, some years ago I had a student looking not at the octonians, but at there's some weird algebras out there once you throw away associativity. And there's something called the Sedonians. And he was looking at a similar construction using the Sedonians. But yeah, there are all sorts of weird things out there one could do. It would be interesting to explore that.
Those probably wouldn't be superpotential algebras. I mean, it's important that they're isomorphic to V.
But if you
Don't
believe
know.
the classification,
Who knows?
they wouldn't be.
Maybe they are, maybe they're not. Don't know.
There's a unique invariant in the third tensor power, is there?
Pardon?
Is there a unique invariant in the third tensor power?
I don't think so. No, I don't think so. Oh,
In the third,
I forget the decomposition of V tensor 2.
yeah, I think that's right.
That
The other
just says
question?
that the 7, because multiplicity is 1 in the square, tensor square.
Pardon?
Multiplicity of 7 is 1 in the tensor square.
Yeah,
That's right.
So then
Yeah, there are 4. It's multiplicity free. Yeah. Well, if there are no other questions, let's thank Paul again.